And actually, we're going to pick up where we left off last week with the mixture problems. I realize those are kind of tricky, and so I figured we'd spend a little bit more time today going over them. And remember, the key to those mixture problems is getting the formula set up. Once we get the formula set up, we've done enough solving equations that we can handle solving them to get a correct answer. But what we have is we have two ingredients. We have ingredient A and ingredient B that we are combining to get a desired result. And ingredient A and B and the result, of course, have a concentration, which is a percent, and a volume or a weight, depending on what we're given. And remember, the amount of medicine or active ingredient has to be conserved. So what we have for ingredient A plus ingredient B has to equal the total amount of that medication or active ingredient in our result. So let's take a peek at an example again and see how much we remember from last week. So let's say that you need 16% solution. You'll be asked how much 12% solution should you mix with 120 milliliters of 18% solution to get the desired 16%. So the question here is, what percents are in our ingredients here? Well, we have 12% being mixed with 18%. I purposely worded that problem a bit backwards from what we were doing last week because it's a little tougher to pick out the ingredients here. But we are mixing 12% with 18%, and we are hoping to get what percent? We need 16%. Good. So we have the concentrations. Next is to look and see about what our volumes or weights are. In this case, we're given volume, 120 milliliters. Which one does that go with? The 18%. So now we have to look and see which one we're going to make X and how we're going to define the other, because we can only have one variable. It's easiest, since we're given the amount of one of the ingredients, it's easiest if we just make the amount of the other ingredient be X. So then the amount of the result, the 16%, is just going to be X plus 120. So now we can write out our equation. Remember, the amount of active ingredient is what we're focusing on in our equation, or the amount of the medication. And that is the concentration times the volume, or the mass, depending on what we have. So 12% is 0.12 times X, plus 18% is 0.18 times 120. That's going to have to equal 16% is 0.16 times X plus 120. So our first step, there's nothing to combine with the 0.12x. 0.18 and 120 are going to combine to give us 21.6 equals 0.16 times x is 0.16x. 0.16 times 120 is 19.2. And now we just have an equation to solve. We have x on each side, so I have to get rid of one of them. Which one are we going to get rid of, the 0.12 or the 0.16x? We get rid of the smaller one, the 0.12. So that's gone. All we have left is 21.6x on the left side. We have to take 0.12x away from the other side as well. We're going to take, the only thing we can take it away from is the other x's. So from the 0.16, so 0.04x. And we still have the plus 19.2. Then what do we do? Subtract 19.2. Good. So 2.4 equals 0.04x. And then to get x by itself, it's being multiplied by 0.04. We divide by 0.04. Giving us 60 equals x. So now we have to go back up, make sure we've answered our question. X represents the amount of the 12%. So that's 60. The units here are milliliters. So this is 60 milliliters. And we're asking how much of the 12% solution. So the 60 milliliters is what we're looking for. Now, just out of curiosity, how many of you did the homework on this and felt good about it? Show of hands. Okay, that's kind of why I wasn't expecting many hands to go up there. So let's do. I'm gonna put one up here, and I'm gonna have you guys give it a shot and see if you can work through it now after seeing one example, another example, and see how it goes, and then we'll talk about them a little bit more. So what I'm gonna put up here is, I'm going to word it a little bit differently. You have 38% and 58% solutions. How much 58% do you need to mix with 240 milliliters of 38% to create 43% solution? So I want you to try this in your notes. I'm going to pause the recording for you. I'll give you a few minutes, see if you can set it up. Then we'll take a look at setting up the equation, and we'll go from there. Let's just take a peek and see if you're getting it set up right. So our two ingredients, we're going to combine. So we have the 38% and we have 58% being mixed together. And we're hoping to get a result of 43%. So now our volume, we're given 240 milliliters of the 38%. So we'll let x be the volume of the 58%. So 240 plus x, or x plus 240, it doesn't matter. I tend to think better with the variable first. So this combines to give us an equation. 0.38 times 240 plus 0.58 times x equals 0.43 times x plus 240. Now I'm going to pause here. Show of hands, how many people got to that equation? Okay. How many people have no idea where that equation comes from? Okay.
I got it, but is it really crucial if you have the 0.58x swap with the 0.38 by 240?
Yeah, if you had the 0.58x and then plus 0.38 240, that makes no difference. That'll be the exact same thing. Okay, so the key is you have to have the amount of medication or active ingredient from each of the ingredients added together to get the total in your result. And so the amount of that is always going to be your concentration, which is your percent converted to a decimal, times your volume or your mass. So for the two things that are being combined will always go on the left side. Doesn't matter what order, whether you put the 0.38 or the 0.58 first. My mind's just kind of linear, compulsive, so I always put the smaller number first, but it really doesn't matter. So then for each of the ingredients you list its percent converted as a decimal, and then you list the weight or the mass, weight, or volume of what you're combining. Then on the right side, you have the concentration of what you want the desired result to be times the total volume from the other two. So this volume here, x plus 240, is always found by taking these two volumes and adding it together. So now from this point, we would solve the equation. .38 times 240 is 91.2 plus 0.58x. Over here we got to distribute through the parentheses. 0.43 times x is 0.43x. 0.43 times 240. $103.2. Now we're solving. We're going to get rid of one of the x's. Now, actually, I'm going to pause here. From this point, if you were to get to this point in the equation, how many of you are confident you could solve this equation to find the value of x? Okay, that's good that most of us are comfortable from there. So the first thing you have to do is you have to get the variable to a single occurrence of the variable. It appears twice here, so you have two possibilities. If they're on the same side, you can combine them, but here they're not. If they're on opposite sides like they are here, you have to get rid of one of them. So we're going to get rid of the smaller one, which is the 0.43. So we subtract 0.43x and it's gone. We subtract 0.43x from the other side. On the right side, all that's left is the positive 103.2, so 103.2. Over here, the 91.2 isn't going to change. 0.58x minus 0.43x is a positive 0.15x. Now this is just a two-step equation, so we're going to solve for x by subtracting 91.2. So 0.15x equals 12. And we divide by 0.15. X equals, what was that, 80? So you go up here, X is the amount of the 58%, or units are milliliters, so that's 80 milliliters of the 58%. So that's one of the big applications of our equations that we have in medical math. I want to take some time then to look at some of the other applications of equations. And actually, I want to look at one other type that we haven't really checked out for a mixture problem yet. Let's do this. Let's say we need 28% solution and have only 42% solutions. How much, I'll use this abbreviation again, NS, neutral solution or normal saline, should we combine with 300 milliliters of 42% solution? So again, what are the two things, what are the ingredients we're combining here? Well, we have 42%. What are we combining it with? NS, neutral solution, which is what percent medication? 0%. That's why it's neutral solution. It contains no medicinal value. It does not alter the concentration of the medication at all. And we want to get a 28% solution. This problem looks complex because we don't have that second percent. But once we realize that second percent is 0, is a concentration of 0, the rest of the problem is actually a lot simpler, because when you have zeros in there, certain things are just going to disappear. So we have 300 milliliters of the 42%. So the amount of the 0% is going to be X. So then how much of the 28% are we going to need, are we going to get as a result? X plus 300, or 300 plus X. So now as we write this out, 42% is 0.42 times 300 plus 0% is 0 times X. See that? Going to multiply to make X. Or make 0, sorry. So that's going to be gone. And 28% is 0.28 times our X plus 300. So now we can simplify. 0.42 times 300 is 126. This again is 0, so it's gone. We don't have to worry about it. Equals 0.28 times X is 0.28X. 0.28 times 300 is 84. And now it's just a matter of solving this equation. So we'll subtract 84. So this is 42 equals 0.28x, and we will divide by 0.28. X equals 150. So that's 150, our units we've been using our milliliters of basically sterile water, neutral solution. So we've looked at a couple of applications of our variables. You know, one application was just working with it as a name and manipulating the symbols. The second application we saw here was in an equation where it had a value. We just had to figure out what the value was. The third application we want to look at now is in a formula. And in a formula, it might be something as simple as a temperature conversion, like degrees Celsius is equal to 5/9 times degrees Fahrenheit minus 32. So what's happening here is these variables, the C and the F, don't have values right now. They're waiting to be given a value. And once in any formula, once all of the variables except for one have been given a value, then we can find that last one by using the solving equations methods we looked at last week. Generally, we use a formula that's set up neatly like this. So if we were this formula here would be used if we wanted to find the temperature in degrees Celsius given the temperature in degrees Fahrenheit. Just to make it easy on ourselves, right? If we wanted to find the temperature in degrees Fahrenheit, we would find a different formula that was F equals, so it'd be easier to do. So let's take a look. Let's say that we have 98.6 degrees, which is human body temperature, degrees Fahrenheit, and convert that into degrees Celsius. So we are now going to substitute in, we're going to evaluate this formula for F is 98.6. We replace the F with the number 98.6. And now it's just a matter of order of operations. We have to do what's in the parentheses first. 98.6 minus 32 is 66.6. Then 5/9 times 66.6 is 37. So that, like I said, that is our third function of a variable, is it's sitting there waiting to have a value given to it so we can use it. Other formulas we run into, well, we saw the perimeter formula last week when we were learning how to solve equations. Perimeter of a rectangle is 2 times the length plus 2 times the width. So the same here. You might be asked to evaluate for P when L equals 7 and W equals 5. So evaluate for P means P is the one I'm not going to be given the number for. I have to find that. L equals 7, so instead of 2 times L, I replace the L with 7. So 2 times 7 plus 2W will become 2 times 5. I replace W with 5. And again, it's now just order of operations. 2 times 7 is 14. 2 times 5 is 10. So I add those together to get 24. One that might be a little bit more important for us. Might look like this. The formulas don't necessarily have to be set up with just a single letter in there for the variable. You can have whole words. Often it makes more sense to have the whole words written out. Pounds is equal to 2.2 times kilograms. So if I am told that a patient is 40 kilograms, how much do they weigh in pounds? Well, I am going to abbreviate that now with P and K. P is equal to 2.2 times, replace kilograms with 40. And all we have to do is multiply out. 2.2 times 40 is 88. So that patient would be 88 pounds. We can use the formula the other direction. So we got P equals 2.2K. And for this formula, in fact, it's more often used in the other direction. So let's say we were told that the patient weighs 110 pounds. We want to find their weight in kilograms. So we can put the 110 in for P equals 2.2K. Now it's just solving an equation for K. It's been multiplied by 2.2, so we divide by 2.2. To get that 50 equals K. So a patient that was 110 pounds is 50 kilograms. Another one we hear a lot about lately, the last several years, BMI, body mass index, is found by taking your weight in pounds divided by your height in inches squared. So you square the height, then multiply by 703. So let's say we have a patient that comes in that is 160 pounds, and let's say they are 68 inches tall, 5'8". Let's find their body mass index, their BMI. So for the weight, we can put in the 160. That's already in pounds. The height, well, I gave you the height in inches, so I don't have to convert feet to inches. So that's 68. I have to remember that's got to be squared times 703. This is a formula where we can actually just enter all this in the calculator in one single line. Because of the way this is set up, since there's only really one piece on top and one piece on bottom of the fraction, I can actually enter it like this, as 160 divided by 68 squared times 703, instead of having it as a fraction like that. So on my calculator, I can just enter 160 divided by 68 squared times 703. That patient has a BMI of 24.33. Which is pretty close to average for the United States, but it is considered above a healthy weight or a healthy index. I'll let you guys try one. So for a patient that comes in with a weight of 80 kilograms and a height 72 inches. Now I'm going to stop you before you start going the wrong direction. Remember, the BMI formula is weight over height squared times 703. But what units does the weight have to be in? Pounds. So we have our formula that pounds is equal to 2.2 times kilograms. You have to do that first to get the weight in pounds. I'll give you a second to figure that one out. So first step, 2.2 times 80 gives us 176 pounds. So now our BMI is 176 over 72 squared times 703. And 76 divided by 72 squared times 703. So 23.87. Any questions? Okay. So on to the next step. We solved some of these equations last time, and we saw here in these formulas, like when we wanted to find the kilograms when we were given the pounds, that sometimes the formula isn't set up in the direction we'd really want it to be in order to put numbers in and solve it. So for something like that, where if pounds equals 2.2 kilograms, most of the time we have patients that come in that know their weight in pounds, or they take their weight in pounds, and we have to convert it to kilograms. So it'd be much more useful for us to have a formula that said kilograms is just equal to something that I can do to the pounds, multiplied by a number, divided by a number, or whatever. So it'd be nice to be able to take a formula like this and rearrange it so that it can be one of the other variables equal to and then a formula. So here we have pounds equals 2.2 times kilograms. So what I'm going to do is I'm going to treat the k, that variable, as an x for right now, and I'm going to try to get everything else away from it. So p equals 2.2k. All that's keeping k from being by itself right now is the 2.2. The 2.2 is multiplying k, so to get rid of it, I have to divide. So I'm dividing by 2.2, and that gives me my k all by itself. Well, I have to do the exact same thing on the other side. Divide by 2.2. So p divided by 2.2 equals k, or k equals p divided by 2.2. I could write it as a fraction like that, or I could write it as just p divided by 2.2 like that as well. That was a relatively simple formula. We had seen a formula earlier that said I could find the temperature in degrees Celsius from my degrees Fahrenheit by doing this, plugging the degrees Fahrenheit in here for F, subtracting 32, and then multiplying by 5/9. What if I have a case where I'm going to take a lot of temperatures in degrees Celsius and I'm going to have to convert them into degrees Fahrenheit? So I'm going to have to solve them for, well, it'd be nice to be able to plug in the numbers for C and just calculate F and not have to solve an equation every time. So I'm going to solve this equation for F. Now, if there were numbers here for C and I was solving this, normally I would take this 5/9 and I would distribute it. Multiply the F, multiply the negative 32. I'm going to save myself a little bit of time here, and I'm going to cheat just a little bit. Right now, what has happened to F is 32 was subtracted from it. And then after the 32 was subtracted, it was multiplied by 5/9. And I'm going to treat it that way. I'm going to start out by dividing by 5/9. So the 5/9 is gone. All that's left over here is the F minus 32. Now, on the other side, I divided by 5/9. When I divide by 5/9, remember, dividing by a fraction, we multiply by the reciprocal. So C divided by 5/9 is equal to C times 9/5, the reciprocal of 5/9. So that is 9/5 times C, or 9/5 C. Now what's still keeping the F from being by itself? Well, the minus 32. How do we get rid of, what's the opposite of subtraction? We add 32. So over here, it's just F. If I have 9/5 C plus 32, what do I get? Well, it's a trick question. It's 9/5 C plus 32. I cannot combine them because this is a C and this is a whole number. They have different names. So if I have my temperature in degrees Celsius, I can find my temperature in degrees Fahrenheit by just plugging in the Celsius temperature here, multiplying by 9/5 and adding 32. And most of the time I would finish this off by putting the F first. F equals 9/5 C plus 32. You could change it to 1.8. It really doesn't matter. The reason I leave it as 9/5 because if I had to go the other way to solve it for C again, 5/9 would be 0.555555555 as a decimal. So you can't, as that form is 5/9, you can't have it as a decimal. So I always leave it as a fraction either way so I can go back and forth between them easy enough. Okay, well, let's look at a little bit more complex spot. Let's say that we have a formula like power is equal to, actually let's do this, P. Let's say that in a circuit we know that the resistance of a circuit is equal to the power divided by the voltage squared. And I want to solve this for P. Well, right now, P is on this side, and it is not by itself. It has the V squared there. How is V squared attached to the P? It's divided. So to get rid of it, we have to multiply by V squared. I'll cancel that out. So over here, I canceled out the V squared. All I have left is P. R times V squared is R times V squared, or RV squared. So P equals RV squared. That one wasn't so bad, but what if I look at that same formula, R is equal to P over V squared, only this time I want to solve for V. So far, every time we've solved for a variable, the variable has been either a whole number or in the numerator of the fraction. Here we were solving for P, but that was in the top of the fraction, in the numerator. We have not solved for something that was in the denominator of a fraction or something we were dividing by. In this case, we are dividing by the V squared, or the V squared is in the denominator of a fraction. So we have to take a couple extra steps before we solve. The first thing we have to do is we have to get the V out of the bottom of that fraction. We can't solve for something we're dividing by. Now that's a V squared, so I'm going to have to do the whole V squared. I'm multiplying by V squared to get it out of the bottom of the fraction. Now you'll see here that's exactly what we did to solve the other one for P. So we get to this same point. Now I can start solving for my V here. And it only looks like there's one thing to get rid of, but there's actually two things. When this equation was built, in this form, V was first squared, taken to the exponent of 2, or power of 2, and then it was multiplied by R. So when we go to take this apart, or to solve it, we're first going to divide by R, since that was the last thing that was done to build the equation. So we divide by R, so it's gone. What's left here is V squared. P divided by R, well, we can't really combine the letters, so we're just going to write it as P over R, P divided by R. Remember, a fraction and a division problem can kind of be swapped back and forth. And now that we have that, what's left to get rid of on the V? The squared. What's the opposite of squaring something? Square rooting it. So we can do a square root. So the square root and the squared cancel out to leave us with V. On the other side, we have to be careful to make sure we square root the whole thing. So it's simply the square root of P over R. So V equals the square root of P over R. So here you have M equals L over 4TC. Solve that for C. I'm going to pause it and give you a chance to do that in your notes. So the first thing we have to do is we have to get C out from underneath the bottom of that fraction. Depends on what tactic you take. Some people would multiply by the whole 4TC. Did anybody do that? Show of hands. One of you? A couple of you? Okay. That works fine. Multiplied by the whole 4TC. Now this is gone. We just have L here and this is 4mtc, or m times 4 times t times c. To get c by itself, then you have to divide by 4mt. So you get c equals L over 4mt. And conceptually, that's probably easier to understand. Because you divide it by the whole thing, it goes on bottom. Some would approach this, and it's probably the way I would attack it, by just multiplying by c to get it out from underneath the bottom. So m times c is just mc, and over here the c is gone. This is L over 4t. If you did it this way, the next step is a little bit more difficult. Like I said, doing it this way over here, there's nothing on the bottom, so you just divide by everything and put it on the bottom of the fraction. Here we have to get rid of the m, so we divide by m. We're left with c here. Well, L over 4t divided by m, treat that as m over 1, becomes L over 4t times 1 over m. So L times 1 is L. 4t times m is 4tm or 4mt, either way. This is just a little bit conceptually harder to combine the L over 4t divided by m. But either way you did it would have been fine as long as you come up with this. Now notice, here on bottom I have 4mt, here I have 4tm. It really makes no difference. It's the same thing. As long as I'm multiplying those three together, the order they're in does not matter. Okay, it is time for our break. We went a little past here. It's 11:22. Let's try to come back a little after, like 11:30, 11:31, and we'll start our second half.